It drifts through space without light, without heat, and without any visible sign that it was once a star. This object is small, dense, and ancient. Its surface temperature is only a few degrees above absolute zero. It no longer emits visible radiation. No fusion burns at its core. Gravity holds it together, but nothing inside pushes outward anymore. It is almost indistinguishable from the darkness that surrounds it. Around it, the universe has grown quiet. Galaxies are dim. New stars no longer form. Motion itself has slowed, stretched across unimaginable spans of time. In this era, change happens so gradually that it feels like stillness. Objects drift for trillions of years without encountering anything else. This is a black dwarf, not a black hole. Not a failed star, but the cold, final remnant of something that once shone. Its mass is compressed into a sphere no larger than a planet. Matter inside is packed so tightly that ordinary atoms no longer exist in familiar form. Time has erased all remaining heat, leaving behind a stellar core that has surrendered its last energy to the expanding universe. No black dwarfs exist yet. The universe is still far too young. To reach this state, time must advance far beyond the present. Beyond the lifespan of stars, beyond the age of galaxies, trillions of years must pass before a star like this can cool completely into darkness. And this particular black dwarf has a history. Long before it became cold and silent, it was warm and luminous. It once shaped the space around it. Planets formed in its presence. Energy flowed outward from its core in a steady, life-sustaining stream. This black dwarf was once a familiar star. It was once the sun. To understand how a star that fills the sky with light can eventually become a dark, drifting remnant, we must travel backward through time, tracing each slow transformation that led here. The story of the sun does not end in darkness. It unfolds into it. In the beginning, there was no sun. There was only darkness and cold, a vast expanse of space where nothing seemed to happen at all. Somewhere in this ancient void, roughly 5 billion years before the present moment, a cloud began to exist. Not a cloud of water vapor like those that drift across Earth's skies, but something far more fundamental and lonely. This was a molecular cloud, a collection of hydrogen atoms bonded together into molecules, mixed with grains of dust so fine that they would be invisible to human eyes even if magnified 1,000 times. The temperature here hovered just above absolute zero, perhaps 10 degrees above it. The darkness was so complete that it seemed absolute. This cloud had no beginning that could be marked with precision. It had always existed in some form, having been created in the furnaces of dying stars billions of years before. The atoms within it had been forged in stellar cores, scattered across space by ancient explosions, and allowed to drift and cool for eons. Now they existed in this molecular cloud, compressed gently against one another by the weight of material surrounding them, yet still so diffuse that the entire cloud might span many light years across space. If a being from Earth were to stand within this cloud, they would see nothing but darkness, feel nothing but cold, and detect no sound whatsoever, only the patient presence of matter existing in the vacuum. The molecular cloud was not perfectly uniform. Somewhere within its vast expanse, there existed slight variations in density. In one particular region, the hydrogen molecules were just slightly more concentrated than in the surrounding area. This was not a dramatic difference. It was a subtle accumulation, the result of countless random collisions and gravitational attractions over millions of years. Yet this small variation would prove to be the most consequential difference in the history of an entire solar system. It is often thought of as a force that pulls objects downward, But this understanding is incomplete. Gravity is actually a property of all matter. Every atom, every molecule, every speck of dust possesses a gravitational attraction to every other particle in the universe. In the vast emptiness of space, this attraction is infinitesimally small between individual atoms. But when billions upon billions of atoms gather together, the combined effect becomes noticeable. The slightly denser region of the molecular cloud possessed a slightly stronger gravitational attraction than its surroundings. This meant that material from the less dense regions around it was very slowly, almost imperceptibly, drawn toward the dense center. This process was extraordinarily slow. The molecular cloud had no mechanism to accelerate the collapse. There was no external force pushing inward, no magnetic field suddenly reorganizing, no nearby supernova blast wave compressing the cloud. The collapse happened because gravity, patient and eternal, was stronger in the denser region than in the surrounding area. Material drifted inward at speeds measured in fractions of a kilometer per second. It would take millions of years for any noticeable change to occur. An observer watching this cloud would see no visible transformation for a human lifetime or for thousands of human lifetimes. Yet the process was inexorable. Once it began, gravity ensured its continuation. As material fell inward, the density of the central region increased. As density increased, gravity became stronger. As gravity became stronger, more material fell inward faster. The process began to feed itself, though still at the leisurely pace of cosmic processes. This was the beginning of what astronomers call gravitational collapse. Slow, patient transformation from a distributed cloud to something more condensed and concentrated. Around it, other molecular clouds drifted through the cosmic void. The galaxy itself rotated majestically, carrying all these clouds along its disk. The molecular cloud containing our future solar system moved through space at speeds of hundreds of kilometers per second relative to distant stars. And yet this motion was so vast that no individual change would be visible over mere centuries or millennia. The universe is vast beyond comprehension, and the timescales at which it operates are equally incomprehensible to creatures who live for decades. Inside the collapsing region, the gravitational potential energy of the falling material was being converted into other forms of energy. As atoms and dust grains fell inward, they moved faster than they had before. This increased speed represented kinetic energy, the energy of motion. Yet energy cannot be created or destroyed, only transformed. The gravitational potential energy that had been stored in the distributed cloud was being transformed into the kinetic energy of inward falling material. This transformation process generated heat as a side effect. Particles collided with increasing frequency as the density rose. These collisions transferred momentum and energy, gradually warming the material. But at this early stage, the warming was minimal. The collapse was still so gradual, and the material was still so diffuse, that the temperature rose only slightly from its initial near absolute zero state. Radiation could easily escape from the cloud, carrying away the heat generated by gravitational collapse. The cloud remained cold, appearing as a dark silhouette against any background light, completely obscured by the dust within it that blocked visible light from passing through. Yet unseen, the machinery of stellar formation was gradually awakening. The molecular cloud began to rotate very slowly. This rotation likely originated from the random motions of particles within the original cloud, amplified by the conservation of angular momentum as the cloud collapsed. Angular momentum is a fundamental property of any rotating system. The same principle that causes ice skaters to spin faster when they pull their arms inward. As the cloud collapsed from a large size to a smaller size, its rotation rate had to increase to conserve the same amount of angular momentum. This rotation, though slow by human standards, would eventually become significant. The timescale of this pre-stellar phase stretched across hundreds of thousands of years, perhaps even millions. During this entire period, no fusion occurred, no light was generated, and no energy was released except through the gradual conversion of gravitational potential energy into heat and motion. An external observer with instruments sensitive enough to detect infrared radiation might have noticed the cloud becoming very slightly warmer. The dust grains within it would have been emitting faint heat radiation. But to any being relying on visible light alone, the collapse would have been completely undetectable. As the collapse continued, the cloud structure began to change. Material was no longer distributed uniformly. Instead, it accumulated more densely toward the center. The cloud began to develop a structure with a denser core surrounded by a more diffuse outer envelope. Around this core, a disk of material began to form, fed by infalling material from the larger cloud. This disk would not stabilize or become important for some time yet, but already the basic architecture of a future solar system was beginning to take shape in the invisible darkness. The cold persisted throughout this phase, though the interior was beginning to warm incrementally. Temperatures in the outer envelope of the collapsing cloud might have risen to only a few dozen degrees above absolute zero. In the very center, where the material was most concentrated, temperatures might have reached 100 degrees or more above absolute zero. By the standards of the universe at large, these were blazing infernos. By the standards of human experience, they were the coldest environments imaginable. This contradiction captures something essential about the cosmos, that the universe operates on scales and with intensities utterly foreign to human intuition. The dust grains themselves underwent changes during this phase. Some of them began to clump together as gravitational attraction and occasional collisions brought them into closer contact. The collapse accelerated. After millions of years of almost imperceptible change, the process began to move noticeably faster. The core of the collapsing cloud had become significantly denser, and as density increased, gravity grew stronger. Material from the outer envelope fell inward more rapidly now, where once the infall took place at fractions of a kilometer per second, velocities increased to kilometers per second. Yet by the standards of human experience, or even by the standards of events on Earth's surface, this remained extraordinarily slow. The central condensation grew warmer as the gravitational collapse accelerated. More and more material accumulated in the center, and as it fell inward, it was compressed by the weight of all the material outside it. This compression is similar to what happens when a gas is squeezed. It becomes denser and hotter. The interior of the collapsing cloud, once merely cold, began to achieve warmer and warmer temperatures. Radiation was released from the compression itself. Some of this radiation began to heat the surrounding material. The cloud was no longer completely cold and dark, though no visible light was yet being produced. At this stage, the object at the heart of the collapse is called a protostar. A protostar is not yet a true star, for it does not yet produce energy through nuclear fusion. Instead, it generates energy purely through gravitational contraction. Continued infall of material releases gravitational potential energy, which is converted into heat and radiation. This process can sustain for hundreds of thousands of years, providing enough energy to warm the protostar's interior to millions of degrees even as no fusion occurs. The disk of material surrounding the protostar became increasingly important during this phase. As material fell inward from the outer cloud, it often possessed some sideways velocity component in addition to its inward motion. This sideways motion is the result of the cloud's rotation. Because of the conservation of angular momentum, this rotation rate increased as the cloud collapsed. The effect was that infalling material could not fall perfectly straight inward. Instead, it curved away from a direct path, forming a rotating disk around the protostar. This disk was not a peaceful, orderly place. Friction between the material in the disk, turbulence created by temperature gradients, and magnetic forces all contributed to complex motion within the disk. The friction was particularly important because it allowed energy and angular momentum to be transferred outward through the disk. Material near the protostar, which rotated very rapidly due to the strong effects of angular momentum conservation in the small radius, was slowed down by friction with material further out. Conversely, material further out was accelerated. This transfer allowed material to gradually spiral inward while angular momentum was transported outward. The temperature at the center of the protostar rose steadily. This was not a uniform rise. The interior became far hotter than the surface, and a temperature gradient developed, with the center being very hot and the outer regions being cooler. The material at the protostar's center began to achieve temperatures of hundreds of thousands of degrees. At these temperatures, matter no longer exists in the form that humans would recognize. The atoms were completely ionized, their electrons torn away by the violent thermal motion. The material became a plasma, an electrically charged fluid of ions and free electrons. The protostar began to emit significant radiation. This radiation emerged primarily in the infrared portion of the spectrum, invisible to human eyes, but easily detected by sensitive instruments. An astronomer with the right equipment could have observed this protostar during this phase as a dim infrared source, growing gradually brighter as the gravitational collapse continued and the interior temperature rose. To the naked eye, looking toward the location where the protostar existed, there would still have been nothing visible, only darkness. Yet the darkness was no longer complete. Energy was being released, heat was spreading outward, and the stage was being set for the next transformation. The heating was not uniform throughout the protostellar mass. The interior, where pressures were highest, achieved the highest temperatures. The outer envelope remained cooler and more tenuous. This temperature gradient drove convection within the protostar. The hotter, less dense material from the interior wanted to rise, and cooler, denser material from the outside wanted to sink. These convection currents would have stirred the protostar's interior, mixing material and transporting heat outward. The rotation of the entire object affected these convection patterns, causing them to develop organized structures aligned with the axis of rotation. The mass of the protostar grew steadily as material from the surrounding disk fell inward. Where once the condensed region contained the mass of perhaps a few Jupiters, it now accumulated the mass of tens of Jupiters, then hundreds. The gravitational attraction grew correspondingly stronger, drawing in material even faster. The process was self-reinforcing. More mass meant stronger gravity, which meant faster infall, which meant more mass accumulation. It would take roughly 100,000 years for most of the material to accumulate from the surrounding cloud. Magnetic fields played an important but complicated role during this phase. The original molecular cloud had possessed a weak magnetic field, inherited from the larger galaxy. As the cloud collapsed, this magnetic field became compressed along with the material. The conservation of magnetic flux meant that the field became progressively stronger. This strengthening magnetic field began to exert forces on the charged particles in the hot plasma at the center of the protostar. These forces could resist or redirect the inward motion of material to some extent. In some cases, magnetic fields could channel material into a narrow stream that spiraled inward along the field lines rather than falling uniformly inward from all directions. The rotation of the protostar became more pronounced as the collapse continued. The original molecular cloud had been rotating very slowly, imperceptibly slow. But as it contracted, angular momentum was conserved. The rotation rate had to increase to compensate for the decreasing size. The protostar, containing most of the cloud's mass, but occupying a much smaller volume, rotated much faster than the original cloud had. Yet even at this stage, the rotation was not fast enough to cause the protostar to fling material outward. Gravity remained strong enough to hold everything together. The surrounding disk also rotated more rapidly. The inner portions of the disk, closer to the protostar and in regions of stronger gravity, rotated faster than the outer portions. This differential rotation created shear in the disk, adjacent layers of material moving at slightly different speeds. Shear can generate turbulence, which can in turn generate magnetic fields through a process called the dynamo effect. These magnetic fields further influence the motion of material in the disk, creating an extraordinary, complex interplay of gravitational, hydrodynamic, and magnetic forces. Heat was being transported outward from the protostar's interior through radiation and convection. Some of this heat escaped into the surrounding space, radiated away as infrared light. This radiation loss was essential, for without it, the interior temperature would have climbed even faster. As it was, the temperature rose at an impressive rate, doubling or tripling over the course of perhaps 100,000 years. The infrared luminosity of the protostar increased correspondingly. To a distant observer with infrared instruments, the protostar would have appeared to be growing noticeably brighter around the protostar, in the disk and in the outer envelope. The temperature gradients created regions with different chemistry. In the hotter inner regions, volatile compounds that could remain as gases only at high temperatures were vaporized. Closer to the protostar's center, even these were broken down into atoms. In cooler outer regions, volatile compounds could remain as solids or liquids. These chemical variations would later prove crucial in determining the composition of planets that would form in different regions of the disk. The protostar's mass at this stage was approaching the mass of the present-day Sun. Most of the material that would eventually become the solar system was now concentrated in this central object. Yet nuclear fusion had still not begun. The interior temperature, though, it had risen to millions of degrees, was not yet hot enough for hydrogen nuclei to fuse. That threshold was still ahead, waiting to be crossed as the collapse continued and the density and temperature rose further. This phase of development lasted roughly 100,000 years, brief moments in cosmic timescales, yet longer than the entire existence of human civilization, measured from the present day backward. During this 100,000 years, the future of the entire solar system was being shaped. The amount of material that would become the Sun was being determined. The initial rotation rate of the Sun was being set. The structure of the protostellar disk from which planets would eventually form was being established. All these factors would have profound consequences for the solar system's eventual architecture. The temperature at the center of the protostar continued to rise. It had reached 5 million degrees, then 10 million. The pressure at the core had also climbed astronomically. The weight of all the material above the center was pressing inward with a force that would crush any human object instantly. The density in the core had increased so much that a single cubic centimeter of material would weigh as much as a large building on Earth's surface. Under these conditions, hydrogen nuclei, single protons, were in constant, violent collision with one another. A proton is the nucleus of a hydrogen atom, a particle so small that billions of them could fit on the point of a needle. Yet protons, being positively charged, repel one another with an electric force. For two protons to fuse together, they must collide with enough energy to overcome this repulsive force and get close enough that the strong nuclear force can take over. The strong nuclear force is far more powerful than the electric force at very short ranges, but it acts only over incredibly tiny distances. The barrier to fusion is crossing the gap between the range of the electric force and the range of the strong nuclear force. At 10 million degrees, the protons in the core of the protostar were moving fast enough that collisions could occasionally overcome this barrier. Sometimes, when two protons collided head-on with exactly the right energy, they would manage to get close enough for the strong nuclear force to bind them together. When this happened, a miracle occurred. Two hydrogen nuclei merged into a single nucleus containing both protons and neutrinos, but it released energy on a skeljakom per Henke end. The energy released in a single fusion reaction was millions of times greater than the energy released in a chemical reaction like burning. At first, these fusion reactions occurred only rarely. For every billion collisions between protons, perhaps only one or two resulted in successful fusion. Yet there were so many protons in the core inimaginably many, more than could be counted, that even this tiny fraction resulted in a substantial number of reactions per second. These reactions began to contribute meaningfully to the heat generated in the core. The energy released by fusion began to push back against the gravitational force compressing the core inward. For the first time, there was a force inside the protostar that was working against gravity rather than simply being compressed by it. As the fusion reactions released more and more energy, the temperature in the core rose slightly. This temperature increase meant that collisions between protons became even more energetic. More collisions succeeded in overcoming the fusion barrier. The rate of fusion reactions increased. This increase in fusion rate meant that even more energy was released per second. This energy heated the core further, which increased the fusion rate further. A positive feedback loop developed, but unlike the positive feedback that had driven the gravitational collapse, this one pushed against gravity rather than amplifying it. Within a relatively short period, perhaps a few years or decades, a remarkable equilibrium was established. At some point during this transition, the inward push of gravity was balanced by the outward push of the radiation and heat generated by nuclear fusion. At that moment, the gravitational collapse halted. The protostar stopped contracting. The temperature and density in the core stabilized at levels where the rate of energy generation by fusion exactly matched the rate at which energy was being radiated away into space. This was the moment of the sun's birth. The birth of the sun was not a sudden event marked by an explosion or a bright flash. Instead, it was a transition from one state to another, from a protostar continuously collapsing under gravity to a star in hydrostatic equilibrium, where gravity and radiation pressure balanced perfectly. An external observer watching the event would have noticed no particular moment when the transition occurred. The infrared brightness would have continued to increase gradually. The temperature would have continued to climb slowly. Yet at some point during this gradual change, the sun ceased to be a protostar and became a true star. The sun at its birth was not identical to the sun of today. It was dimmer because the fusion rate at its core was lower than it would eventually become. The surface temperature was lower than it would be after it had settled into stability. The interior temperature was lower, for the core had not yet achieved the extreme density and temperature that would develop over billions of years. Yet already, the fundamental mechanism of the sun's existence was in place. At its core, hydrogen nuclei were fusing into helium. This process would continue for the next 10 billion years, sustaining the sun's luminosity and controlling its fate. The reaction through which the sun generates its energy is called the proton-proton chain reaction. It begins when two protons fuse to form a nucleus containing one proton and one neutron. This nucleus is called deuterium, an isotope of hydrogen. In the process, one of the original protons transforms into a neutron, releasing a positron and a neutrino. The positron quickly collides with an electron and annihilates, releasing pure energy. The deuterium nucleus then captures another proton, forming a nucleus with two protons and one neutron. This is an isotope of helium. Finally, two of these helium-3 nuclei collide and fuse, releasing energy and forming a helium-4 nucleus with two protons and two neutrons. The net result of this chain of reactions is that 4 hydrogen nuclei are combined into one helium nucleus. The helium nucleus is lighter than the 4 original protons, and this missing mass has been converted into energy according to Einstein's famous equation, E = mc². Because the speed of light is such a large number, even a tiny mass corresponds to an enormous conversion of hydrogen into helium in the sun's core releases enough energy to sustain the sun's luminosity, keeping it shining brilliantly into space for billions of years. The energy generated in the core must somehow reach the surface to be radiated away. This is accomplished through 2 main mechanisms: radiation and convection. In the core itself, where temperatures exceed 10 million degrees, energy is transported primarily through radiation. Photons are continuously emitted, absorbed, and re-emitted by the material in the core. Each time a photon is emitted, it carries energy outward. Each time it is absorbed, it transfers that energy to the material where it is absorbed. Through this process of constant emission and absorption, energy gradually diffuses outward from the core. The process of radiative transport is indirect and slow. Photons are produced in the core, but they do not travel straight outward to the surface. Instead, they are absorbed almost immediately by the surrounding material and emitted in a random direction. The next photon produced might go outward, inward, or sideways. This random walk process means that it takes a very long time for energy to travel from the core to the surface. In fact, a photon created in the very center of the sun will take millions of years to travel to the surface, not because light moves slowly, but because it is constantly being absorbed and re-emitted in random directions. The neutrinos produced in the proton-proton chain escape directly into space without interacting significantly with the sun's material. They carry away a small fraction of the energy released in fusion, about 2%. The rest of the energy is retained and contributes to heating the sun. This energy heats the solar material, increasing its pressure and temperature. The increased pressure pushes outward, counteracting the inward pull of gravity. The result is the stable, balanced configuration called hydrostatic equilibrium. The newly born sun was surrounded by its protostellar disk, still containing the material that had not yet accreted onto the sun itself. This material included dust grains, small planetesimals that had formed through dust grain collisions, and leftover gas that had not yet been incorporated into the sun. This disk would be the site where planets would eventually form. The sun's radiation and solar wind, stream of charged particles flowing outward from the sun, would influence the disk's evolution. The inner regions of the disk were hotter, while the outer regions were cooler. This temperature difference would prove crucial in determining the composition of planets that would eventually form in different locations. The newly born sun rotated much faster than the present-day sun does. It completed a rotation every few days. This rapid rotation was a consequence of the angular momentum it had inherited from the original molecular cloud. Over billions of years, interactions between the sun and its own magnetic field, combined with the loss of angular momentum to ejected material, would gradually slow this rotation. But at birth, the sun was a rapid spinner, with a more active and violent magnetosphere than it would later develop. The sun's brightness at this moment was about 70% of its present-day brightness. This is known as the faint young sun paradox. Sun was definitely dimmer when it was young. This fact created challenges for the early Earth, for a dimmer sun provided less warmth. Yet evidence from ancient rocks suggests that liquid water existed on Earth's surface even during this time. This apparent contradiction was eventually resolved through the understanding that the early atmosphere contained more greenhouse gases than the present-day atmosphere, providing additional warming to compensate for the sun's dimness. The transition to the hydrogen-burning state was achieved relatively quickly in cosmic terms. The entire process from the beginning of significant gravitational collapse to the stabilization of hydrogen fusion took perhaps 1 million years, blink of an eye in cosmic timescales, yet an eternity by human standards. During this million-year period, the region around the solar system was transformed from a cold, dark molecular cloud to a system centered on an active star with a warm, bright protostellar disk surrounding it. The stage had been set for the formation of planets. The sun settled into a new rhythm now, one that would define most of its existence. It had entered what astronomers call the main sequence, the stable hydrogen-burning phase of stellar life. But unlike the mature, balanced sun that Earth would come to orbit, the early main sequence sun was somewhat turbulent and wild. The fusion reactions in its core, while now generating enough energy to support the sun against gravity, were still adjusting to the conditions created by the sun's internal structure. The result was a young sun that was notably more active and more variable than it would later become. The surface of the young sun was significantly hotter than the present-day sun's surface, not because of a different core temperature, but because the core fusion rate was higher. When hydrogen fuses into helium, the reaction releases the same amount of energy per reaction. But in the young sun, more reactions were occurring per second because the core was denser and hotter than it would eventually become. This higher energy production meant that higher luminosity was required to transport the heat from the core to the surface. Higher luminosity means more radiation flowing outward, which means a hotter surface. The young sun's luminosity was approximately 70% of what it would be when Earth was formed, and the sun was only a few tens of millions of years old. The difference in luminosity seems modest, only 30% dimmer, but on a planetary surface, the difference in warmth received from the sun is substantial. Earth, had it existed at this point and orbited where it does today, would have received roughly half the warmth it actually receives from the present-day sun. The surface would have been frozen, despite being at the same orbital distance from a star. The fact that the sun has grown gradually brighter over its lifetime is an important factor in understanding the history of life on Earth. The young sun's surface temperature was about 5,600 Kelvin, slightly hotter than the present-day sun's surface temperature of 5,778 Kelvin. This difference of about 200 degrees might seem insignificant, yet it corresponds to noticeably different radiation properties. The young sun's radiation was shifted slightly toward the blue end of the visible spectrum compared to the present-day sun. An observer looking at the young sun would have seen a very slightly more blue-white color compared to the yellow color of the sun today. The difference would have been subtle. Most observers would not notice it at all, but it was real. The young sun's interior structure was different from the present-day sun's interior structure. The core was smaller and denser. The zone where hydrogen was fusing was more sharply defined. The radiative zone, the region between the core and the outer layers, occupied a larger fraction of the sun's volume. The convective zone, the region near the surface where energy is transported by convection rather than radiation, was correspondingly smaller. This different interior structure would gradually change over time as hydrogen was consumed in the core and the products of fusion accumulated. The young sun possessed a much more active magnetic field than the present-day sun. The magnetic field is generated by the motion of hot, electrically conducting plasma in the solar interior. The faster rotation of the young sun meant that this plasma was moving more rapidly. Rapid motion of conducting material generates stronger magnetic fields through a process called the dynamo effect. The young sun's rotation was about 10 times faster than the present-day sun's rotation, completing a full rotation in approximately 2 to 3 days. This rapid rotation drove a strong magnetic field, which in turn drove vigorous solar activity. The manifestations of this solar activity were clearly visible on the young sun's surface. Sunspots were more numerous and more persistent than they are on the present-day sun. These are temporary regions on the solar surface where the magnetic field is particularly strong, causing the affected region to be cooler than its surroundings. Although cooler, they emit more energy into the surrounding atmosphere through magnetic heating, making the sun's upper atmosphere hotter and more active. Solar flares, violent explosive events in the solar atmosphere, occurred more frequently on the young sun than on the present-day sun. These flares released enormous amounts of energy in short periods of time, occasionally liberating as much energy in a few minutes as the entire solar surface generates in an hour. The solar wind, stream of hot plasma flowing outward from the solar atmosphere, was much stronger from the young sun than from the present-day sun. The solar wind is driven by the heating of the solar atmosphere, and the more active young sun had a hotter atmosphere. This stronger wind would have swept outward through the protoplanetary disk, influencing the motion of dust and small particles. The stronger wind would have gradually pushed lighter elements and volatile compounds outward, affecting the chemical composition of the inner solar system. The young sun's corona, the outermost layer of the atmosphere, was hotter and more extended than the present-day solar corona. The solar corona is heated by the dissipation of magnetic energy, and the strong magnetic field of the young sun meant that more energy was available for heating. The coronal temperature reached millions of degrees, similar to the present-day coronal temperature, but the corona was more energetic overall. X-ray and ultraviolet radiation poured outward from the young solar corona at rates far exceeding the present-day sun. This intense radiation would have had profound effects on any planets or planetary atmospheres that existed in the young solar system. The ultraviolet radiation, in particular, can break apart molecules in planetary atmospheres. The intense solar wind can strip away lighter atmospheric gases. These effects would have been much stronger in the young solar system than they are today. A planet like Venus, if it had existed at that time, would have been subjected to far more intense atmospheric erosion than it is today. This may help explain why Venus lost its water, not because of gradual processes over billions of years, but because of aggressive atmospheric loss during the sun's early, active phase. The sun's mass loss rate during this phase was higher than it is today, though still modest. Stars continuously lose mass through their stellar wind streams of particles flowing away from the star's surface. The young sun's stronger wind meant that more mass was lost per unit time. Over the course of a billion years, this would add up to a significant amount, perhaps 1% of the sun's total mass. Yet even losing 1% of its mass would not have dramatically altered the sun's evolution. It would have had only a modest effect on the sun's luminosity and only a slight effect on the orbits of any planets that existed. The young sun continued to generate energy at a steady rate through hydrogen fusion in its core. Unlike the variable activity on the solar surface, the core fusion process was remarkably consistent. The core maintained a nearly constant temperature and pressure as long as hydrogen was available, and as long as the energy generated in the core balanced the energy radiated from the surface. The rate of hydrogen fusion was completely determined by the temperature, density, and composition of the core. Because these properties changed only very slowly, the core fusion rate changed only very slowly, the sun's overall luminosity increased gradually, at a rate of perhaps 1% per 100 million years. The protoplanetary disk surrounding the young sun was undergoing its own evolution during this phase. Dust grains in the disk were colliding with one another, sometimes sticking together through electrostatic forces and sometimes bouncing apart. Over time, the collisions resulted in the accumulation of dust grains into increasingly large objects, first millimeter-sized, then centimeter-sized, then meter-sized, then kilometer-sized. This process of dust accumulation would eventually lead to the formation of planets, though that process would take several more million years to complete. In the inner solar system, where the temperature was hot, only rocky materials and metals could condense into solid form. Volatile compounds remained as gas and were pushed outward by the solar wind. In the outer solar system, where it was cold, volatile compounds like water, methane, and ammonia could condense into solid form. These differences would determine the composition of the planets that eventually formed. The inner solar system would develop small, rocky planets. The outer solar system would develop larger planets with thick atmospheres of hydrogen and helium, surrounded by layers of ice and rock. The young sun of this epoch was entering the longest stable phase of its existence. For the next several billion years, it will burn hydrogen in its core, increasing gradually in luminosity and temperature, but maintaining essentially the same overall structure and character. The violent surface activity and rapid rotation would gradually diminish over time as the sun spun down through magnetic braking. But the fundamental process of hydrogen fusion would continue uninterrupted, sustaining the sun's luminosity and maintaining its stability. This phase is called the early main sequence because it occurs early in the sun's total main sequence lifetime. A more accurate term would be the young main sequence phase to distinguish it from the middle, aged main sequence phase that would follow. The early main sequence phase is characterized by this combination of active surface phenomena, rapid rotation, high luminosity relative to the later sun, and continuous adjustment of the solar interior as hydrogen is consumed and helium accumulates. This phase lasted approximately the first billion years of the sun's life. After that, the sun would enter a more sedate and stable phase that would persist for the next several billion years. Billions of years had passed, and the sun had matured into a remarkably stable and predictable object. The turbulent youth was behind it now. The rapid rotation that had characterized the young sun had gradually slowed through a process called magnetic braking, where the sun's magnetic field interacted with the solar wind to transfer angular momentum away from the sun. The fierce magnetic activity that had generated countless solar flares and ejected intense radiation had moderated into a more regular rhythm. The surface temperature remained steady at approximately 5,778 Kelvin, a number that would vary by only a few degrees over the course of a billion years. At this stage in its existence, the sun had settled into a pattern of extraordinary consistency. Each day, the same nuclear reactions occurred in its core, billions upon billions of times per second, fusing hydrogen into helium with perfect reliability. The energy generated in the core traveled outward through the radiative zone, where it was absorbed and re-emitted countless times, gradually diffusing toward the surface. This journey took millions of years for individual photons, but the process was so consistent and so well established that the energy flow had become nearly perfectly predictable. The sun's luminosity varied by less than 1% from year to year, from century to century, from millennium to millennium. The middle-aged sun that now existed was approximately 4.6 billion years old, roughly the present age of the actual sun in our universe. At this point, the sun had consumed roughly half of the hydrogen in its core through fusion. The half of the helium that had been produced from this fusion had accumulated at the core's center, gradually increasing the core's composition from pure hydrogen to a mixture of hydrogen and helium. This accumulation of helium was a slow process, but it had profound consequences for the sun's structure and future evolution. The helium is denser than hydrogen, and it does not participate in the proton-proton chain reaction that generates energy. Instead, it accumulated passively in the core. The accumulation of helium was causing a subtle but important change in the sun's interior structure. The core, where hydrogen was still fusing into helium, was becoming increasingly a shell around a helium core rather than a uniform region of hydrogen fusion. The hydrogen that remained in the core was concentrated in a spherical shell surrounding the helium-rich center. This hydrogen-burning shell was where the sun's energy was still being generated as more and more helium accumulated, the proportion of the core occupied by this burning shell decreased. The effect of this gradual change was that the core was becoming progressively denser. Helium is about 4 times heavier than hydrogen for the same volume, so a core with more helium would be denser if the mass distribution remained the same. But the accumulation of helium was causing more than just density changes. It was also affecting the gravitational balance within the core. The increased density meant that the gravitational pressure at the center of the Sun was becoming stronger. To maintain hydrostatic equilibrium, the temperature and pressure throughout the core had to adjust. The result was a very gradual increase in the core temperature and density. This increase in core conditions was causing the hydrogen fusion rate to climb slowly but steadily. The rate of nuclear reactions is extremely sensitive to temperature. A small increase in temperature results in a much larger increase in reaction rate. This sensitivity is described mathematically through an exponential relationship. A 1% increase in core temperature results in roughly a 5% increase in the fusion rate. Over billions of years, the cumulative effect of this temperature increase was significant. The Sun's luminosity was increasing at a rate of roughly 1% per billion years. This might seem minuscule, but over billions of years, it amounted to a substantial brightening. The increase in solar luminosity was having profound effects on planetary systems. On Earth, this gradual brightening had been a crucial factor in the evolution of life. As the Sun grew brighter, the amount of heat reaching Earth's surface increased. Without compensating changes in Earth's atmosphere or surface reflectivity, the average surface temperature would have risen steadily. Yet Earth's life and geology had adapted in response to this gradual brightening. Early in Earth's history, when the Sun was dimmer, the atmosphere must have contained higher concentrations of greenhouse gases like carbon dioxide and methane to keep the surface warm enough for liquid water. As the Sun brightened over billions of years, these greenhouse gases were gradually removed from the atmosphere through geological and biological processes, maintaining a relatively stable climate. The middle-aged Sun maintained a regular cycle of surface activity with a period of approximately 11 years. This is the solar cycle, during which the number of sunspots varies from a maximum to a minimum and back to a maximum. During maximum periods, sunspots were numerous and large. Solar flares were frequent. The solar corona was particularly bright and active. Then, over the course of several years, the solar activity would decline, reaching a minimum where sunspots were rare and small. The total energy output of the Sun varied slightly over this cycle, but the variation was tiny, only about 0.1% from the solar maximum to the solar minimum. Yet even this tiny variation had effects on Earth's climate, contributing to century-scale variations in weather patterns. The solar cycle arises from the way the Sun's magnetic field is generated and maintained. Differential rotation, the fact that different latitudes on the Sun rotate at different speeds, with the equator rotating faster than the poles, causes magnetic field lines to become stretched and twisted. Over time, this stretching and twisting creates increasingly complex magnetic field configurations. Eventually, the magnetic field becomes so tangled that it can no longer be contained. It erupts, releasing energy and contributing to increased surface activity. After the eruption, the process begins again, eventually leading to another cycle of magnetic accumulation and release. In the middle-aged Sun's interior, the radiative zone remained relatively unchanged in structure. This zone extended from the core, where temperatures were above 10 million degrees, outward to a radius of approximately 0.7 times the Sun's surface radius. In this zone, energy is transported primarily through radiation, the emission and absorption of photons, rather than through the bulk motion of material. The material in the radiative zone is so dense and hot that it is completely ionized, consisting of free electrons and positive ions rather than neutral atoms. The photons produced in the core are constantly being absorbed and re-emitted, gradually diffusing outward. Surrounding the radiative zone was the convective zone, a region extending from the bottom of the radiative zone outward to the Sun's visible surface. In the convective zone, energy is transported primarily through convection, the bulk motion of material. Hot, less dense material rises from below, carrying energy outward. Cooler, denser material sinks from above, carrying away energy. The result is a circulation pattern of rising and sinking material, similar to the convection patterns in boiling water or in the atmosphere of a planet. The convective zone is where sunspots form, where the solar magnetic field is most active and dynamic. The boundary between the radiative zone and the convective zone, called the tachocline, was a region of particular interest. This thin layer is where the greatest changes in rotation rate occur. The radiative zone rotates as a solid body, with all parts rotating at the same rate, while the convective zone shows differential rotation. This contrast in rotation rates creates shear that helps generate and maintain the Sun's magnetic field. The interaction between the radiative and convective zones at the tachocline is crucial to understanding the solar cycle and the long-term behavior of the Sun's magnetism. The Sun's surface during this middle, aged phase showed relatively little change from year to year or century to century. The photosphere, the visible surface, maintained a temperature of 5,778 Kelvin. Sunspots came and went with the 11-year cycle. Granules, regions where hot material is rising from below, covered the surface with a pattern that looked somewhat like the cells in tissue, each granule perhaps 1,000 kilometers across. These granules were constantly being created as new material rose from the interior, lived for approximately 5 to 10 minutes, and then sank back down. The granular pattern at any given moment was temporary, but the process was eternal and unchanging. Above the photosphere was the chromosphere, a thin layer approximately 2,000 kilometers thick, where temperature actually increases with height, contrary to what one might expect. The chromosphere is the source of much of the Sun's magnetic activity, hosting small-scale prominences and jets of material that periodically erupt outward. The chromosphere's temperature increases to several thousand Kelvin near its top, reaching values comparable to the photosphere's temperature despite being much less dense. This temperature increase is still not fully understood, though it is likely related to the dissipation of magnetic energy. Beyond the chromosphere was the corona, the outermost layer of the Sun's atmosphere. The corona extends millions of kilometers into space, though it is far too thin to be visible except during a total solar eclipse, when the photosphere's bright light is blocked and the corona's glow becomes apparent. The coronal temperature is millions of degrees hotter than the surface below it, a counterintuitive fact that has puzzled solar physicists for decades. The extreme temperatures in the corona seem to contradict the expectation that it should be cooler farther from the heat source. The resolution to this paradox involves the dissipation of magnetic energy in the corona, though the exact mechanism remains an active area of research. The middle-aged Sun's mass remained essentially constant, having lost only a tiny fraction of its original mass through the solar wind over the course of billions of years. The mass loss rate from stellar winds in a mature star like the Sun is approximately 1 billion kilograms per second, an enormous number by human standards, yet utterly insignificant compared to the Sun's total mass of 2 septillion kilograms. At this rate, the Sun would need to lose material for approximately 30 billion years to lose 1% of its mass. Since the Sun has existed for only about 4.6 billion years at this point, it has lost far less than 1% of its initial mass. The Sun's interior remained in perfect hydrostatic equilibrium, with the outward pressure from the hot interior exactly balancing the inward pull of gravity. This equilibrium was so precise that a change of even 1% in the balance between these forces would have led to dramatic consequences. If gravity was stronger, the Sun would be contracting, growing hotter and brighter. If pressure was stronger, the sun would be expanding, growing cooler and dimmer. The fact that the sun had remained essentially unchanged in size and brightness for billions of years testified to the exquisite balance maintained by the combination of gravity and fusion-generated pressure. Yet subtle changes were occurring despite the overall appearance of stability. The core was becoming progressively richer in helium and progressively hotter. The fusion rate in the hydrogen burning shell was gradually increasing. The sun's luminosity was climbing imperceptibly slowly. These changes were so gradual that they were undetectable to any observer watching for a mere million years or even 100 million years. Yet over the course of a billion years, they accumulated into changes that were real and measurable. The sun's brightness had increased by roughly 1% over the course of its existence to this point, and it would continue to increase at this steady rate for several more billion years. The middle-aged sun was approaching the midpoint of its main sequence lifetime. Approximately 5.4 billion years would remain before the sun would exhaust its core hydrogen and begin the process of transformation toward the red giant phase. During these remaining years, the sun would continue much as it had for billions of years, reliable source of steady energy, gradually brightening but remaining fundamentally stable. For any observers on planets orbiting this sun, the changes would be so gradual that they might not be noticed over the course of thousands of years. Yet over billions of years, the cumulative changes would prove crucial to the long-term fate of planetary systems. The slow, steady brightening of the sun would eventually make it too hot for water to remain liquid on Earth's surface, setting an ultimate limit on how long life could persist there. The moment finally arrived. After billions of years of slow, steady change, the sun's core had reached a critical threshold. The core temperature had climbed to approximately 100 million Kelvin. At this temperature, a new nuclear reaction became possible that would fundamentally transform the sun and its surroundings. The remaining hydrogen in the core had been almost completely exhausted and converted to helium billions of years ago. Now, the helium itself could no longer remain inert. At 100 million Kelvin, helium nuclei possessed enough energy and momentum to overcome the enormous electrostatic repulsion between them and undergo fusion themselves. The process of helium fusion is more complex than hydrogen fusion, requiring 3 helium nuclei to collide and stick together to form carbon. This reaction is called the triple alpha process, since an alpha particle is another name for a helium nucleus. The reaction is extraordinarily slow compared to hydrogen fusion. It requires 3 particles to come together simultaneously, an event that occurs far less frequently than a 2-particle collision. Yet in the incredibly dense core of the sun at this moment, even this rare reaction was happening at a sufficient rate to generate significant energy. The energy released by helium fusion is enormous, and its release occurred suddenly. Unlike the gradual increase in hydrogen fusion that had occurred over billions of years, the onset of helium fusion happened relatively rapidly once the core temperature reached the ignition point. The energy released in the core began to push outward with increased force. The core temperature, already at 100 million Kelvin, began to rise even further in response to this new energy source. Yet the increase in temperature would have one crucial effect. It would slow down the helium fusion rate. This is one of the most remarkable aspects of stellar evolution. As the core temperature increases above the critical temperature for helium fusion, the triple alpha reaction rate actually decreases. This is because the rate of the triple alpha reaction increases extremely rapidly with temperature is even more temperature sensitive than hydrogen fusion. When the core temperature rises above 100 million Kelvin, the reaction rate increases so dramatically that the energy output from helium fusion becomes enormous. This energy causes the core to expand and cool slightly, which then decreases the reaction rate. The result is a self-regulating system where the helium fusion rate adjusts to maintain the core at a temperature around 100 million Kelvin. As helium fusion began in the core, the structure of the entire Sun began to change. The increased energy generation in the core caused a rapid increase in the outward pressure. This pressure began to push the outer layers of the Sun outward more strongly than gravity was pulling them inward. The result was an expansion slow at first, but gradually accelerating. The Sun's radius began to grow. The outer layers, no longer held so firmly by gravity, began their journey outward into space. As the Sun expanded, its surface became larger. The same amount of energy was now spread over a larger surface area. By the inverse square law, the principle that energy intensity decreases with the square of the distance, the intensity of radiation at the Sun's surface decreased. The surface temperature fell. The Sun's photosphere cooled from 5,800 Kelvin to 4,500 Kelvin or lower. This cooling transformed the Sun's appearance. The light it emitted shifted dramatically toward the red end of the spectrum. White or yellow white light gave way to orange, then to deep red. The Sun had become a red giant. The luminosity of the Sun, despite the cooling of the surface, actually increased dramatically during this transformation. This seems counterintuitive. A cooler object should emit less energy, but the key was the enormous increase in surface area. The Sun's radius expanded from approximately 700,000 kilometers to over 100 million kilometers. This increase meant the surface area increased by a factor of approximately 20,000. Even though the surface temperature was lower, the vast expansion more than compensated. The total energy output increased by a factor of thousands. The Sun became a monster of radiation, flooding the inner solar system with heat on a scale billions of times greater than before. The expanding outer layers of the Sun cooled as they moved farther from the hot core. In the cooler outer layers, atoms that had been ionized in the hot interior could now recombine with electrons to form neutral atoms. Molecules could form. Complex chemistry became possible in the outer atmosphere. The Sun developed an extended atmosphere of neutral atoms and molecules extending far into space. This atmosphere was partially transparent, allowing infrared radiation from the hot interior to pass through it and escape into space. The red giant Sun was a place of violent convection and instability. The outer layers were expanding, being pushed outward by the increased pressure from the core. Yet gravity still pulled inward, resisting this expansion. The result was not a smooth, orderly process, but a violent struggle between outward and inward forces. The Sun's surface showed enormous convection cells, some large enough to span 1 million kilometers. The photosphere was more dynamic and chaotic than it had ever been during the quiet main sequence phase. Within the expanding red giant, the core had contracted further, becoming even denser and hotter. The hydrogen that still remained in a shell outside the helium core was being fused at an increased rate, pushed to greater temperatures and pressures by the overlying material. This hydrogen-burning shell was now contributing significant energy in addition to the helium fusion in the core. The combination of energy from both fusion processes drove the enormous luminosity of the red giant. The core and the hydrogen-burning shell were racing against each other in a competitive process. Core was becoming hotter and denser, driving increased helium fusion, which was pushing the layers above it outward. The carbon produced by the triple alpha reaction in the core accumulated at the very center of the Sun. Unlike the helium that had accumulated during the main sequence phase, this carbon could not easily mix with the surrounding material. The carbon was heavy and sank toward the center, accumulating in an ever denser layer. Other fusion products also accumulated. Oxygen nuclei were created when carbon fused with additional alpha particles, and these too sank toward the core. The composition of the sun's core was transforming from pure helium to a mixture of helium, carbon, and oxygen. The evolution of the red giant was not instantaneous. The process of expansion and cooling lasted tens of thousands of years. During this time, the sun would gradually grow larger and brighter, though the exact trajectory of this growth was complicated. The sun did not expand smoothly and monotonically. Instead, there were fluctuations and variations, times when the expansion accelerated and times when it was slower. These variations were related to instabilities in the shell burning. Sometimes the shell would grow very hot and release a burst of energy, driving rapid expansion, and sometimes it would cool slightly and burn more slowly. As the sun expanded, it engulfed the inner planets one by one. Mercury, having orbited so close to the sun, was the first to be consumed. As the sun's atmosphere expanded to Mercury's orbital distance, the planet found itself orbiting within the sun's outer layers. Friction with this thin but extensive atmosphere gradually slowed Mercury's orbit. The planet spiraled inward, eventually being consumed entirely by the sun's interior, where it was vaporized by the intense heat. Venus followed next, engulfed as the expanding red giant extended its reach farther outward. Earth, orbiting at 1 astronomical unit, the distance from the sun to Earth's present orbit watched as the sun's surface approached closer and closer. The fate of Earth during the red giant phase was sealed. As the expanding sun's surface approached Earth's orbit, Earth would be engulfed by the sun's outer atmosphere. The temperatures in this region would be thousands of degrees, far hotter than Earth's surface could withstand. The planet would be vaporized. Water would boil away and escape into space. Rock would melt and become part of the sun's atmosphere. Any life that had existed on Earth would have been extinct for billions of years already. The sun had become too bright for liquid water to exist on Earth's surface approximately 1 billion years before the red giant phase, long before the sun actually expanded far enough to engulf the planet. The red giant phase would last approximately 1 billion years. During this time, the sun would reach its maximum size, extending to perhaps 250 times its present radius. The radius would be so vast that the planet Jupiter would orbit deep within the sun's outer atmosphere. Yet this enormous size and luminosity would not be permanent. The red giant phase was a transition, a tumultuous reorganization of the sun that would eventually give way to something new. The red giant phase had finally ended. The sun's enormous outer layers had drifted away into space, creating a beautiful glowing cloud called a planetary nebula. What remained at the center was something small, dense, and incredibly hot white dwarf. Imagine taking the entire mass of the sun and squeezing it down to the size of Earth. That is what a white dwarf is. The density of a white dwarf is almost beyond understanding. 1 teaspoon of white dwarf material would weigh as much as an elephant. A piece the size of a sugar cube would weigh thousands of tons. The atoms in a white dwarf are crushed together so tightly that the electrons are packed into their smallest possible quantum states. They cannot be compressed any further without violating the laws of quantum mechanics. This quantum resistance to compression is what holds the white dwarf up against its own gravity. It is not fusion, and it is not pressure from hot gas. It is the fundamental resistance of matter itself to being squeezed into the same space. The white dwarf was incredibly bright despite its small size. The surface temperature was around 100,000 Kelvin, roughly 17 times hotter than the sun's surface. This extreme heat made the white dwarf glow with an intense white-blue color. Most of its light was in the ultraviolet range, invisible to human eyes, but the small amount of visible light was blindingly bright. If you could somehow stand nearby without being vaporized, the white dwarf would appear as an intensely bright point of light, more brilliant than any star in the night sky, despite being no larger than a planet. This intense heat came from the gravitational energy released when the sun's core contracted during the red giant phase. As the core collapsed inward, converting gravitational potential energy into heat, temperatures soared to millions of degrees. This stored heat was now slowly escaping into space through radiation. The white dwarf would remain hot for an incredibly long time, trillions of years, gradually cooling as it radiated away its energy. Inside the white dwarf, strange things happened. The interior was actually cooler than the surface, which is the opposite of what happens in normal stars. The material was so dense that it behaved like a crystal rather than a gas. The carbon and oxygen nuclei formed a lattice structure, while the electrons moved freely around them at extremely high speeds, nearly at the speed of light. This was matter in a state that does not exist anywhere on Earth. The white dwarf did not shine through nuclear fusion. There were no reactions occurring inside it. The carbon and oxygen were chemically inert at the temperatures and pressures within the white dwarf. Instead, the white dwarf simply radiated away the heat it inherited from its violent past. Each second, it emitted enormous amounts of energy into space, yet this energy was drawn from a finite reserve. As time passed, the white dwarf would gradually cool, becoming dimmer and dimmer. The rotation of the white dwarf was very slow. During the red giant phase, the expanding material had carried away most of the sun's angular momentum. The white dwarf spun slowly, perhaps rotating once every few hours or even more slowly. The magnetic field of the white dwarf was also quite weak compared to the field the sun had possessed during its more active phases. The violent activity that had characterized the young sun was now completely absent. Around the white dwarf orbited the remaining planets. Jupiter, Saturn, Uranus, and Neptune continued their eternal cycles, orbiting in the dim light of their dying star. The heat they received was now vastly reduced compared to what they had received when the sun was in its main sequence phase. The outer planets, which had always been cold, became even colder. Any heat that the planets possessed was now slowly radiating away into the frigid void of space. The white dwarf existed in a state of perfect silence. No wind blew from its surface. No flares erupted. No sunspots came and went with their 11-year cycle. The dynamic, changeable sun that had once filled the solar system with light and activity had transformed into something static and unchanging. The only change occurring was the slow, imperceptible cooling as the white dwarf gradually released its stored thermal energy. This cooling process would take an almost unimaginably long time. After 1 billion years, the white dwarf would still be very hot and very bright, though somewhat dimmer than it had been initially. After 1 trillion years, it would have cooled to perhaps 10,000 Kelvin and would be much dimmer. Yet even after trillions of years of cooling, the white dwarf would still be warm. The time required to cool completely would be roughly 10 to the 15th power years, 10 quadrillion years, vastly longer than the current age of the universe, which is only about 14 billion years old. The composition of the white dwarf was primarily carbon and oxygen, the products of helium fusion in the core during the red giant phase. Heavy elements created near the end of the red giant phase, such as neon and magnesium, would have sunk toward the center. The lightest elements, such as hydrogen and helium, were gone. They had been blown away in the planetary nebula and the stellar wind. What remained was the ashes of nuclear fusion compacted into this incredibly dense object. The surface of the white dwarf was smooth and featureless. There were no mountains or valleys, no storms or weather patterns. The surface was a cooling crust of crystalline material, slowly radiating heat into space. Sometimes, if a companion star were orbiting nearby and transferring material onto the white dwarf, explosive thermonuclear reactions could occur in the transferred material, creating temporary bursts of brightness. But the sun's white dwarf had no companion star. It orbited alone through space, gradually cooling into obscurity. The white dwarf would eventually become a black dwarf, an object so cool that it no longer radiates any significant heat and becomes essentially invisible. This process would take so long that no black dwarfs are believed to exist anywhere in the current universe, since no white dwarfs have been cooling for long enough. The universe is not yet old enough for any white dwarf to have cooled completely into a black dwarf. But given enough time, trillions upon trillions of years, that is what the white dwarf would eventually become. For now, though, the white dwarf remained a testament to what the Sun had been. It contained the accumulated mass of billions of years of nuclear fusion, compressed into a space no larger than a planet. It was both a spectacular object and a melancholy one, the final remnant of a star that had once filled the sky with light and warmth. The era of the active Sun was completely past. A new era of slow, inexorable cooling had begun. After an unimaginably long time, so long that it is almost impossible to comprehend, the white dwarf finally cooled completely. The surface temperature had gradually fallen over trillions of years, dropping degree by degree, century by century, millennium by millennium. The radiation escaping into space had dwindled from the intense ultraviolet and visible light of the early white dwarf phase to infrared, then to longer and longer wavelengths. Eventually, the white dwarf had cooled to the point where it was no longer hot enough to radiate any significant energy into space. This object, no longer a white dwarf, for it no longer glowed white or emitted significant radiation, became something new. Astronomers call it a black dwarf. A black dwarf is not black in the sense of absorbing light. Rather, it is an object so cool that it barely emits any radiation. It would be essentially invisible, detectable only through its gravitational influence or if it happened to pass in front of a distant star. The black dwarf was still fantastically dense, still composed of carbon and oxygen crystal, still possessing the mass of the Sun squeezed into the volume of a planet. But it had become cold, dark, and silent. The surface temperature of the black dwarf had fallen to perhaps 5,000 Kelvin or lower, no hotter than a cool main sequence star surface. But unlike a main sequence star, the black dwarf was not generating any new energy. It simply radiated away the last remnants of its thermal energy at an incredibly slow rate. Billions of years might pass with the black dwarf's temperature dropping by only a single degree. It was the astronomical equivalent of a dying ember, glowing faintly, cooling inexorably toward absolute zero. The universe at this epoch was vastly different from the universe of the present. Most stars had long since exhausted their fuel and become white dwarfs or black dwarfs themselves. The bright, active stars that filled the night sky, the universe that had existed for the first 10 or 20 billion years, had largely faded away. The universe had become a much darker, colder place. The cosmic microwave background radiation, the afterglow of the Big Bang that still filled all of space, had cooled to nearly absolute zero as the universe continued to expand. Space itself was growing cold. This era is called the degenerate era, a time when the universe is dominated not by active stars, but by the remnants of stars, white dwarfs and black dwarfs, slowly cooling into the darkness. The universe had become a vast, mostly empty realm, populated by billions upon billions of these cold stellar remnants, each one isolated and alone, orbiting slowly through the ever-expanding cosmos. Any planets that had survived the death of their parent star orbited these cold remnants, receiving almost no heat. These worlds were incredibly cold, far below the freezing point of water, buried in perpetual darkness. On the timescales of the degenerate era, the universe operated in a way that was almost incomprehensible to beings used to thinking in terms of years or centuries, or even millions of years. 1 trillion years might pass more time than the entire age of the current universe, with seemingly nothing happening. The black dwarf remained at essentially the same temperature. The orbital period of the orbiting planets continued unchanged. The cosmic microwave background radiation continued to cool at an imperceptible rate. Change was happening, but it was so slow that it would be completely invisible to any observer watching for any reasonable period of time. Yet change was happening. The black dwarf was still radiating away energy, still slowly cooling. The universe was still expanding, growing larger and emptier and colder with each passing eon. Particles were decaying through processes called proton decay and other exotic processes that occur on timescales of quintillions of years. Matter itself was slowly transforming, breaking down into its component particles through mechanisms that we do not yet fully understand. The universe was on a journey toward a state of ultimate emptiness and cold, a state called heat death. The orbits of planets around black dwarfs were not perfectly stable on these timescales. The universe contained many black dwarfs, and their mutual gravitational attractions were slowly causing the stellar remnants to move through space. Sometimes, a black dwarf would approach another black dwarf closely enough for planetary orbits to be disrupted. A planet orbiting one black dwarf might be captured by another, or it might be ejected entirely into the emptiness of interstellar space. These processes operated over tens of billions or trillions of years, but eventually they would affect every stellar system. The surface of the black dwarf remained crystalline and rigid. The interior remained at incredibly high density, still supported by quantum degeneracy pressure. As the black dwarf cooled, it actually contracted very slightly, becoming marginally smaller and denser. This contraction released a tiny amount of gravitational energy, which was radiated away into space. This gravitational contraction continued happening, century after century, millennium after millennium, even after the black dwarf had become very cold. The cooling process was not perfectly efficient. Some of the gravitational energy released by contraction could not escape quickly and was retained within the black dwarf, causing it to cool more slowly than a simple calculation might suggest. The black dwarf's composition remained unchanged. There were no reactions, no interactions that could transform the carbon and oxygen into anything else. The material had become completely inert, chemically frozen in time. Even the atomic nuclei within the black dwarf were stable. The only process that might eventually change the composition was the exotic process of proton decay, if protons are indeed unstable, as some theories suggest. But this process, if it occurs, operates on timescales of quintillions of years or longer, far beyond the timescale we have considered so far. The universe during the degenerate era was profoundly different from the universe today. Almost no visible light was being produced anywhere. The cosmos had become a dark place, illuminated only by the incredibly faint radiation from scattered black dwarfs, the ancient radio waves left over from the most distant and earliest events, and the cosmic microwave background radiation cooling toward absolute zero. To an observer in this future universe, the night sky would not be filled with stars. Instead, it would be almost completely dark, empty and cold beyond comprehension. Yet even in this cold, dark universe, the black dwarf continued its existence. It drifted through space, following the gentle curves of space-time warped by its own mass and the mass of other stellar remnants around it. It orbited no sun, as it had no parent star anymore. It was not orbited by any planets, assuming those planets had been scattered away billions of years earlier by gravitational interactions. The black dwarf was alone, a cold, dense sphere of crystalline carbon and oxygen, cooling at an imperceptible rate, existing in a universe that had become almost as cold as itself. The future of the black dwarf extended forward into a time span so enormous that it becomes almost meaningless to discuss it in terms of numbers. If we were to count every second that had elapsed since the Big Bang until now, and then multiply that number by 1 trillion, we would only be beginning to approach the timescales over which the degenerate era would unfold. The black dwarf would exist, cooling slowly, for times that make the 13.8 billion year age of the current universe seem like an instant. Eventually, after time so vast that they strained the ability of language to describe them, other processes would begin to dominate. Proton decay, if it occurs, would slowly transform the black dwarf's matter into lighter elements and energy. The expansion of the universe would continue, eventually causing space itself to become so large that even nearby objects would recede from view. The black dwarf would be surrounded by a completely dark, completely empty void, with no other objects visible, no other sources of light or heat, nothing but emptiness and silence. In this ultimate future, the universe would reach a state of maximum entropy, maximum disorder and randomness. The black dwarf would still exist, still slowly cooling, still containing energy that was slowly radiating away into space. But the universe around it would be so cold and so empty that this radiation would be completely imperceptible. The universe would have become a place of extreme quietness, where virtually nothing changed, where motion had slowed to nearly nothing, where time itself would seem to have almost stopped. The sun, in its journey from a cold molecular cloud to a bright star to a red giant to a white dwarf to a black dwarf, would have experienced a transformation that captures the ultimate fate of all stars. The energy that the sun had radiated outward during its 10 billion year main sequence lifetime, enough energy to warm billions of planets and sustain the existence of life, would eventually be completely radiated away. The matter that had fused in the sun's core, creating the heavy elements from which planets and life itself were made, would cool into inert crystalline form, awaiting the ultimate processes that would eventually transform all matter. This is the far future of the sun, a future so distant that it seems almost like a dream, a black dwarf in an empty, cold, silent cosmos, slowly cooling into the ultimate darkness, representing the final chapter of stellar evolution and the ultimate fate that awaits all stars in a universe that seems destined for heat death. Yet this future is real, and awaits the sun in the incomprehensibly distant tomorrow, after this chapter of cosmic history has finally closed. The soft sound of cosmic silence falls, and nothing moves. Time stretches on infinitely, each moment indistinguishable from the last. The universe has become still, cold and dark, a realm of ultimate tranquility where the active, dynamic processes that once defined the cosmos have faded into memory, leaving only the slow, eternal cooling that will continue until the very end of time itself, or perhaps beyond even that.